what many people have discovered, and is in fact part of the theory of chromatography, is that when you change the flow rate, you can actually maximize your separation using that metric that I showed you in the previous slide. And this, I do not know why chromatographers do this, but they plot separation power down. So the minimum here is actually best separation in this diagram. And this is just a cartoon of rendering by me of what these look like, but the idea is that if you increase your flow, if your flow is too slow, you kind of have crummy separation, and if you increase it, you reach sort of an optimized condition, and then if you continue to increase your flow, it degrades again. So it's kind of a Goldilocks approach to separation. And the reason, there's actually physics behind this nadir here. One is that if it's too fast, then the compounds can't interact with the stationary phase. They're just being swept through. So you don't get separation of one component from another. But if it's too slow, then diffusion will broaden the peaks. So you get kind of killed by longitudinal diffusion in the separation environment. So we look for this happy optimum. Where's my thing? It doesn't like me. I'm going to look at it and it's going to poke me in the eye. No. Well, anyway, so you look for that nadir, and that is what you want to aim for. Yeah.
So that last slide, how is resolution? Is the separation power the resolution?
Yes. Yes. Yeah. So chromatographers use different measures, but this, what I'm really talking about is if you use this measure, your separation distance divided by the width, that'll actually be a higher number as you go to better separation. And so it's a little funny why they plot them downward in these other graphs. That has to do with the rate theory of chromatography and how the mathematics were developed for that. So I don't want to confuse you with that. If you do get into this literature, they tend to plot it this way. Okay, so when you're working with chromatography, you're faced with some choices you have to make. And here they are. It can be fast, you can have good separation, or you can have really sizable samples, big samples. But you can't have all three. You only get to have two. So for the isotope applications, we actually need kind of big samples because our instruments require enough ions to make a good measurement. And we want good separation for reasons I'll explain later, so we tend to run them at slower separation rates than other systems. And when I put this slide together, it reminded me of one of my first mentors, besides my dad, in science, who was Tom Herring. And Tom, I worked for him as an undergrad, and he taught me many important lessons, one of which was shoot first, ask questions later, which was really valuable because when I went to work for John Hayes for my PhD, his philosophy was ask all the questions you can think of and then some more and then shoot. So it was a really, really terrific, nourishing of a young mind with lots of different ways to think about science. Tom is famous for this diagram. In any analytical method, you can have only two off of this diagram of good, fast, or cheap. If you can't have all three. So I find that. So an homage to Tom. All right, so now we've separated our compounds, we've burned them up, we're sending the compound products into the mass spectrometer, and we've got this problem that we've got a lot of carrier gas going into an instrument that was designed to have really low vacuum, right? Really low pressure, or high vacuum, low pressure. So there's been some modifications based on the original sort of mid-20th century instruments that allow us to accommodate this flow of gas. And they start with what's happening in the ion source. In the ion source, you have neutral molecules. They come in, and then they get smacked upside the head by a high-energy electron. And that gets them so upset that then they lose their own electron, and they become a positive ion, right? And so that's all very good, but we have now not just the CO2 or the other compounds that we're interested in, we also have this helium in there. So you're making a lot of helium ions as well as the analyte. And so a couple of modifications, just so that you're aware of them, they've kind of opened the source so that it's not so constraining and neutrals can escape. And then the important thing is that there's this differential pumping. And that's illustrated in the next slide. And differential pumping is characterized by two pumps, a big one and a little one. And sorry if I got that no, I'm sorry, this is the big one, and this is the little one. So you have all of the helium plus your compounds coming in here, a lot of neutrals. They get pumped out by the big pump. And then there's a slit, the exit slit at the end of the ion source is the only connection between these two chambers. It's the only physical space where molecules or ions can go through. And so the ions get shot through here, and this is now kept at low vacuum by a second pump that's a little bit smaller than this big one. This one has to be big because it's handling big volumes of neutrals. This has very few neutrals, and it can hold the flight tube in the mass analyzer environment where the magnet is and all that at very low vacuum and very steady vacuum. So it's a way to kind of accommodate these bursts and big flows of helium and keep the business end of the instrument nice and steady. It's not a new technology. It's been around a long time, but it was brought into isotope mass spectrometry in the 1980s when we began working with the continuous flow methods. When I was a student, we wanted to open up these sources. And so I literally, this isn't me, this is just a picture from the web, but I literally took the rings off the source and got a hacksaw and cut holes in them to open up the conductance of the source. They now do that for you commercially, but that was our attempt to kind of open it up, let it breathe a little bit. It's fun. Okay, this is an illustration of the circuitry of a Faraday collector. I just want to say a couple of things about how we handle signal processing slightly differently in these instruments. There's these, of course, where's Sean? You know, who's my hero, right? J.J. Thomson, right? Love this guy. So in his early instruments, he developed initial mass spectrometry using photographic plates and then later replaced them with a Faraday cup, which we now use today, moving us from mass spectroscopy to mass spectrometry. Isn't that cool? So cool. Well, anyway, so the Faraday Cup Collection collects the ions. They come in, and a current is fed to that cup to neutralize the positive ions. So you have electrons kind of coming in to match in quantity the number of positive ions hitting your cup. And you just measure the flow of electrons, which is otherwise known as a current, right? So you're just measuring that as and that's actually what gives you your isotope analysis. So that hasn't changed, but what has changed is how we deal with that incoming information from the flow of electrons. And what happens is that the signal is amplified. So you're actually, a current is measured in, what's a current measured in? Amps? Nanoamps, right? So it's measured in nanoamps. But the thermo instruments give you your signal in volts, right? So you're actually a step removed from what you're physically doing. And the reason you're measuring volts, or it's expressing it to you in volts, is that it's being converted from current to voltage in the circuitry. And then it's actually converted into digits. So it's an analog signal because you're continuously monitoring the current. And then it's converted into digits by a digital converter in the circuitry. And then that is sent on to your software and collected. So you actually end up with discrete points as a function of time, not a continuous signal. And so one of the decisions you have to make is how long do you measure slices of time to collect enough points to be meaningful. And what this has done is allowed for sort of variable counting periods. It's nominally maybe a quarter of a second. We're actually now working with much shorter time periods. We're working with 50 hertz in some of the new work that we're doing. But that slice of time captures a bit of your signal. And remember, your signal is constantly changing because you're working with peaks and valleys. And so you have to think about the integration period that will best capture that variation in a meaningful way. So that's one of the changes that's happening. And then, as I mentioned at the onset, we introduce our standards before and after our sample peaks, not interspersed with them. So that's one of the other big changes. So this illustrates some of the calculations that have to go on with the peaks as they come in. So remember, they're now little points in time because of that voltage to frequency conversion, and we have digitization of the signal. And so the software now looks at that change in the signal as a peak comes in and says, okay, I don't know when a peak starts, so I'm going to have to figure this out. Oh, a peak will start when the slope changes, right? But there's always a little bit of noise in there, so the slope is always changing a little bit. So it's a slope change and an amplitude change, typically. And that triggers the software to start integrating across the peak. So that's one piece. And you can change the slope parameters and the amplitude parameters both before and after the peak and tailor them if you have asymmetric peaks, for example. And then the next part of this is involved in kind of correcting the background, sort of subtracting background signal. And that's done, again, from sort of backing up from before the peak and then doing some calculations of an average and then extending that across the peak itself. And there's a number of now algorithms sort of buried in your software on the commercial instruments. And it's like pulling teeth to get the company to tell you what they actually are. But they're all doing something similar to this. All right. So here's another part of what was really unappreciated before we got into this sort of endeavor of measuring molecules coming out of a GC column. And that is that there's actually a chromatographic effect at the level of isotopes. There's mass sensitivity to the separation process itself. And this is not new. This is well known in that we all know about vapor pressure isotope effects, right? You know that the lighter isotopes of water will evaporate preferentially to the heavy isotopes. It's basically the same thing that's happening as the compounds are sort of moving back and forth between the gas phase and the liquid phase in a chromatograph. And so the software corrects for that by sort of figuring out the offset between the two, the isotope mass and the parent mass. And if there's a time offset, it kind of shifts them back on top of each other. That's illustrated here. So these are peaks coming out, and you can see the ratio in the top shows this high isotope value and then a low isotope value, all for the same peak. So what you're actually seeing here is that the first half of the peak is enriched in 13C and the second half is depleted. And that's because the 13C is actually more mobile under the chromatographic conditions that we worked with here. That varies depending on the setup. And then you just simply sort of pick the top of the peak, and there's a little bit of a time shift between mass 44, or mass 44 is at the top, mass 45 at the bottom, and that time difference is what's shifted, and so the calculations shift so everything lines up, and then the deltas, the ratios and the deltas are calculated.